So we're going to take a look today at what's going on with the end behavior of polynomial functions. And to understand that, we really need to understand big numbers. And do we, as humans, really understand big numbers? I'm going to argue that we don't. So for example, here's 0 on a number line, and all the way over here where the smiley face is, that's 1 billion. And I want you to stop me when I'm at 1 million. So as I slide this smiley face along the number line, stop where you think a million is. Well, since I can't hear you, usually in class kids will stop me here and say, that's a million. And then other kids will insist I keep moving. And I keep moving down the number line and they say, stop right there. That's a million. Because, you know, when I write a million, it's 1, 0, well, I put some commas in, 1, 0, 0, 0, 0, 0, 0. And to get to a billion, I put 3 more zeros, and they're like, that, you know, that's about a third of the... No. If I want to stop at a billion, I need to move this guy all the way down there. Actually, more like there. Why? Because in order to make a million into a billion, I have to multiply it by 1,000. I need 1,000 millions to become 1 billion. So, do we understand big numbers? Probably not. I mean, Jeff Bezos' net worth is about $181 billion. Billion with a B. And since we've been doing so much work with compounding interest, if Jeff Bezos made 10% interest in 1 year, his interest alone, without touching that $181 billion, just his interest would be $18,100,000,000. I mean, that's his interest alone. We don't understand really big numbers because we don't get why that's kind of ridiculous. So why do we need to know big numbers for polynomial functions? Well, let's take a look. Oh, let me cover this up. I should cover this up. Let's take a look at this function right here. Y equals x to the fourth minus 2,000x cubed minus 1,000. I want to know what the end behavior of this graph is. Meaning, does this graph start out pointing upwards or pointing downwards? And does it end pointing upwards or pointing downwards? A more sophisticated or mathematical way of saying that is to look at it this way. As x approaches negative infinity, as we move along the graph to the left, what is the y value doing? Is it going up or down? And then, as x approaches positive infinity, as we move along the graph to the right, what is the y value doing? Is it going up or down? Well, one way we could kind of try to figure out what's going on is to go ahead and put in for x a really big number and see what the output for y is. Is the output positive, which means y would be going up, or is the output negative, meaning y is going down? And it turns out we have a quicker way of dealing with this. I'm going to argue that we don't really need to put in a big number for all the x's. My argument is going to be this, that this is the only term we care about when it comes to the end behavior of a graph. This negative 2,000x cubed, yeah, I know it's a big number, but we just don't care about that or that when we're talking about the end behavior. And let me see if I can convince you that this is true. So let's take a look at a smaller value. Let's, instead of taking it to the fourth power and taking the second number to the third power, let's just take the first number, a big number like a billion, and square it and subtract 2,000 times a big number. Well, if I take a billion and I square it, a billion times a billion, what is that? Well, it's not a billion, it's bigger. It's not a trillion. It's not a quadrillion. It's a quintillion. And if I take that 1 billion squared, which is this absurd number, and I subtract 2,000 times a billion, I subtract 2 trillion, Well, 2 trillion is a big number, but compared to a billion squared, if I did the subtraction, that's nothing. That is absolute. Taking away 2 trillion from this big, we still have 999 quadrillion, 998 trillion, and then a bunch of zeros here. I mean, it's still a massive number. So even though this is a big deal, subtracting 2,000 times x cubed minus 1,000, when it comes to looking at the far extremes of the graph, I'm going to argue that this leading term is the one that matters. So what does that mean for us? Well, let's go in and take a look at how we can find the end behavior pretty quickly. The leading term controls the end behavior. So for example, if I had this polynomial function, and sweet mama, look at the size of it. Well, you'll notice I was pretty creative. See how the subsequent terms after the leading term kind of diminish and go away? That's because if I'm concerned about I'm concerned about end behavior, this is the only term I care about. Because when you take a big number to the 8th power, that number is so massive that none of this other stuff is going to affect the outcome as much as this. So if I'm looking for the end behavior, what I'm going to do is I'm going to take a look just at the leading term. The leading term is 6 times something to the 8th power plus stuff. Now, is this stuff important in the graph? Yes, it is. It is very important for all the wobbling around that the graph is doing. But the leading term really just controls the end behavior. So what I'm going to do is I'm going to let x be a negative number and a big number, and I'm going to let x be a positive number. So when x is negative, what happens? Well, a negative to the 8th power, that's 8 negatives, a negative times a negative times a negative times a negative 8 times 6, that's a positive number. A positive to the 8th power, positive times positive times positive times 6, is also a positive number. So what this tells me is that in my curve, when x is negative, as I move along my curve to the left, my y value is going to end as a positive, going up. And what this tells me down here is as I'm moving along my curve to the right, I wobble around a little bit, but I'm going to end up with my y value going up. Now, all this wobbling in between my end behavior, that's what all this stuff controls. That stuff controls the wobbling. But all I care about right now is the end behavior. So I could say, in this particular problem, as x goes to negative infinity, as we move along this graph heading to the left, my y value is going up. And as I move along this graph to the right, as x is moving towards positive infinity, as I move to the right, the y value is also going up. And that's how we can look at end behavior. So let's do some problems together. I would like you to pause the video and write down these problems and see if you can kind of solve them on your own, and then check back in and see how we did. The first problem we do together, you might need my guidance, but after that, try pausing. So let's take a look at number 1. All right, number 1 just over here. Y equals 2x to the 7th minus 5x cubed plus 6. Again, we've got some wobbling going around here, but the leading term is going to determine what my end behavior is like. So I look at 2x to the 7th, and I've got some stuff that doesn't affect my end behavior. So I test an x that's negative, a big negative, and I test an x that's positive. I let x become negative infinity, and I let x become positive infinity. Well, let's see. A negative to the 7th power. That's a negative times a negative times a negative times a negative, 7 times. I'm going to argue that that's negative. And when I take a negative number times 2, it stays negative when x is positive. So I take this big number, infinity, and I say, okay, a positive number to the 7th power is positive. 2 times a positive number is positive. So I can see as x tends towards, as x is heading towards negative infinity, my y seems to be going down. It is heading down. It is heading down to a negative number. As x moves to the right, as x is tending towards positive infinity, when I let x become a really big positive number, what's my y value doing? It's going up to a positive number. Let's take a look over here. What's happening at this graph? Well, again, I'm gonna focus in on my leading coefficient, my leading term right here, and I'm gonna just ignore the rest. So I say let's take negative 3 and let's look at a negative x raised to the 4th power. And let's look at negative 3 times a positive x to the 4th power. Now I said an even power because I think you're going to quickly decide that when x is even, any negative to an even power, whether that power is 2, 4, 6, 8, 10, 12, is always going to end up being a positive number. And when you take a positive number to an even power, it's also going to be a positive number. Now, what happens when we take a negative 3 times a positive number? Well, we get a negative number. And what happens when we take negative 3 times this we get a negative number. So this is telling me that as x goes to the left, as x goes to negative infinity, as we move along our graph to the left, my y is going down. And as x goes to the right, towards positive infinity, my y value is also going down. And so what this graph would look like is it's going down, and then we maybe wobble around a little bit, and then it goes down on the right side. And we can see that, again, if we just look in here and we say, yep, when x is negative, we end up with a negative y. And when x is positive, we end up with a negative y as well. Now let's take a look at just 2 more problems together. Here's the first. Maybe pause the video and see if you could figure out what's going on. Okay, welcome back. I hope you paused the video. Again, our big focus is on this leading term right here. So it's a negative x to an odd power plus stuff. And again, that stuff is responsible for all the wobbling going back and forth in between the ends. Well, I'm going to take a negative number in for x and a positive number in for x. Now I'm using negative infinity to remind me that it's really big. So what do we have? Well, what's a negative to an odd power? Now that odd exponent of 9, but it could be any odd exponent. 1, 3, 5, 7, 9, 11, any odd. Well, a negative to an odd power is a negative. And a positive to an odd power is a positive. But see this negative out in front? A negative times a negative yields a positive y. And a negative times a positive yields a negative y. So you can see here that as x moves to the left, my y is moving up. And as x moves to the right, my y is moving down. And finally, one more problem for you to take a look at. Try this. And I hope that you ended up getting that in this case, both the y values are going to be pointing down when we start this graph and when we end it. Okay, well, I have a second video for you to watch when you're done with this, and the second video has some guided notes for you to follow along, but I hope this helped you within behavior.